Log on, tune in, find out. Another good idea from Cambridge.
I'm going to be talking today about trying to understand uncertainty in climate model components. And this is work that I've been doing with Peter Challoner at the National Oceanography Center in the UK and Jim Gadiger, who's at Los Alamos National Lab. So I'll talk a bit first about, give an introduction and some motivation to why I'm looking at this problem, the methodology that I'm using, and then also how the experiment is designed, some early outcomes, and then some next steps and some things to think about in terms of this program here. This is a work in progress, so it's not finished work. And my background is as an ocean modeler. So primarily I've been looking at ocean hindcast models in conjunction with satellite and in situ data to look both at to quantify the realism of ocean models and also try to understand the uncertainty and variability of the ocean circulation patterns. So you probably all have seen this plot before. It's from Reichler and Kim, and it's also included in this report that came out of the U.S. Climate Change Program assessment report on the quality of climate models. And what it shows is just the change in the CMIP ensembles from 1 to 3 over the generations of the basically IPCC reports. And you can see the improvement in the models as compared to this green dot that's observations over the time period here. So the size of the dot gives you a confidence limit. The larger the dot, the better it is. And then each dot is a separate model that goes into this calculation. And the index that's plotted here, this I squared, is a sum over a large number of different types of metrics to try to quantify the quality of those models. But what I wanted to point out here is this broad range of solutions from all of these models, that they're not really converging on one answer, and there's still a lot of uncertainty in the response of these climate models. So one of the things that I did early on was just to look at a set of models and look at the heat content in the model and the heat uptake. And these plots show the relationship of the surface height temperature field with the subsurface heat content and the change with respect to time. So it's just a quantity sort of to look at heat uptake. So this is from the control run of CCSM, the 20th century simulation from the same model. This is the Hadley CM3 representation. And then I also looked at the POP 10th of a degree resolution hindcast model with inset forcing. So there's a high consistency in this control run, and it progressively has lower consistency towards the POP 1/10 of a degree resolution model. So what does this mean in terms of how realistic and the uncertainty of the models? So I looked at it compared to observations. And one thing we don't have with observations is a time series of temperature at depth for a long enough period. So I compared it to surface height, which is sort of an integrated quantity of the subsurface information in the ocean. So this is about 15 to 20 years of information. I can't remember the exact time period, something like 18 years of sea surface temperature data and the altimeter surface height data, and looking at the relationship of heat SST to the surface height as a proxy for the heat content of the upper ocean. So then if you can look at the same quantity in the models, so surface height and subsurface and surface temperature, you get a similar set of figures as on the previous slide, showing that the control model has a high consistency between the surface temperature field and surface height. And then the 20th century has somewhat degraded somewhat, and then the Hadley and the Pop 10th of a degree model show similar patterns in their relationship, and they're similar to what the observations show. So I wanted to understand why this is happening, especially between the 20th century simulations, and what causes the differences between those solutions. So this plot just summarizes the information. And you can sort of think of it as heat uptake in the model. So the observations are represented by the stars here. And I've looked at the global quantity, the tropical ocean, the North Atlantic, and then the North Pacific. And you can see for most of the cases, the models are taking up too much heat to everything to the right of the star, except maybe in the North Pacific, where two of the models are not taking up enough heat compared to what this calculation shows. But somewhat surprising is that, to me anyway, is that the Hadley CM3 and the Pop 10th of a degree solution are quite similar in their estimate. The triangle and then the circle, and in some cases, mainly the North Atlantic, the Hadley model is closer to the observation representation of this comparison between height and sea surface temperature as the observations. So it got me thinking, trying to how to quantify various things and to look at why there was this distribution in these models. And I was talking to Peter Challoner at one point, and he was explaining to me his work in climate uncertainty and how he was using advanced statistical methods to look at uncertainty in an energy balance model, and also one of these Earth system models of intermediate complexity. So I was wondering, well, if you could look at the uncertainty in those models, why not just look at a GCM and skip those first things? So that's basically what the rest of the talk is about, of using these advanced techniques to look at uncertainty.
But you're sure that the Hadley model has not been tuned for the heat flux in the Atlantic?
I do not know. So, I mean, possible.
Yeah.
So I can't tell you what exactly they did and what they looked at in the Hadley model. Yeah. Yeah, I mean, it certainly could be, and so that got me thinking about why that is. So this is a feasibility study just to look at whether or not these types of techniques can be used in complex GCMs. And because of computation time and complexity of the problem, what I'm looking at is only the ocean ice components of a climate model. So just to look at uncertainty and how that information, we want to get that information about uncertainty. So if we have some sort of ensemble, you could have either an ensemble of one GCM and multiple realizations of that GCM, or you could have a set of several GCMs. And then you look at some sort of outcome represented by this vector V and try to create a PDF which can be used downstream in some other, like a regional model of some sort or socioeconomic models. So the first way that you could look at uncertainty is just with Monte Carlo methods. And if you use it would create a very large and complex model ensemble. So you'd have a number of runs, and if you can think of this as sort of a perturbed experiment of some sort, and you're varying the inputs in this vector x, and so it can be of various sizes. And this vector x, I'm using it in the broadest sense of a parameter, meaning it could also refer to initial conditions, the model structure, model forcing, as well as the parameters used in the physics of the model. And again, so you would have a set of outcomes created from this large ensemble, and then you can directly figure out what the PDF of the outcomes would be. And this would give you an order of 10,000 or so members that you would be necessary to create this PDF. And that's just impossible for a GCM. So instead of using a Monte Carlo type method, just looking at a complex GCM model plus this thing that statisticians call as an emulator. So again, we have a set of GCM runs with this vector x that we're going to vary, producing a set of outcomes v, and this emulator then will be used to create what we need to look at this to create this PDF here. So one of the keys to this ensemble here is how to design it in a smart way so that you're sampling across the space that you need to look at the outcomes of the expected outcomes that you would get if you did a full Monte Carlo type of thing. So if you design this in a smart way, then supposedly you can have a set of outcomes that are reasonable to use the emulator with. And this then reduces the number of simulations that you need from, say, 10 to order 100. So if you had only 2 parameters that you were varying sort of on the order of 10, and if you have 10 parameters, somewhere about 100 ensemble members that you need. So it reduces the number of realizations coming out of these runs that you would need. So you only need to run a GCM, say, 100 times instead of 10,000. So I'm going to first talk about this design here, and then I'll talk about what it means by this emulator. So we want to have a design that to allow us to have a set of parameters that sample the model, or as statisticians like to call it, simulator space adequately. So you can do it just the first way by just having this set of, let's say, 10 parameters and just permeating them. And that would get some large number of runs that you would need, because this would just expand exponentially. The other way is a statistical technique to sample space. There's a couple of them, maybe there's even more than this. So one's Sobol sequence or Latin hypercube methods. So these are used to span the parameter space and sample it so that you can sample the parameters and their relationship to one another in a sensible way, so that you get a meaningful result in your set of GCM simulations that can be used in the emulator. And I'll just give an example of this. So this is just using the soap ball sequences, and I think this is like a MATLAB routine. So the y-axis is just 0 to 1, and this is the number of runs. The blue line is for 10 runs. The red line is for 20 runs, and the black is for 100. And you can see that how it's trying to sample the space between 0 and 1 across the various numbers of runs. And this is only with one parameter. So if you look at 3 parameters, so we have 1 parameter, 2 parameters, and 3 parameters, then this is sort of the sampling that results in using one of these techniques. So the black dots again are for 100 runs, the red are for 20, and the blue are for the 10 runs. And this is just an example of what that sampling parameter space would look like. So when I can't visualize 10 parameters, but it's trying to sample across that, whatever size vector space that you have. And
what is the criteria? I mean, does this assume any structural stability of the underlying system? Or what is the criteria to sample?
This isn't assuming anything about what the model is. It's just sampling from 0 to 1, and then you when you look at the real parameters, you set your minimum and maximum of the parameter that you're interested in, and then relate it to where it is in that 0 to 1. So I'll explain now about the emulator. So again, we have these set of runs. We have our outcomes, and we're going to use these outcomes here to feed into the emulator as training points then to look at the full PDF. So we have say a climate model, and the outcomes y is equal to some function of this vector x, and x is a vector that has tunable inputs that we've chosen from this design that we've created. So we have a relatively small set of simulations with varying values of x, and we want to build this emulator small f of x. And it has to have the following characteristics: that the true value of y at the points x, and that other points, the distribution should give a mean value for x of x that represents a plausible value. And also the probability should be a realistic view of the uncertainty in the model, such as if you got some sort of outcome, some PDF that was a bimodal distribution, and from previous knowledge you thought that that's not realistic, then it would fail this last characteristic or criteria. So I wanted to go through this decomposition of this emulator process for people who aren't familiar with it. So you have f of x is the outcome from your climate model or whatever model you're looking at, and then approximated by this emulator, a small f of x. And that's equal to this Gaussian process that has a mean process of m of x equals 0, and then a covariance portion. The mean process then is consistent of a vector of regression coefficients and this coefficient vector b. And this information is a prior that goes into the emulator calculation. And for the cases that I'm looking at, this is actually a linear function. And then the Gaussian process consists of a variance quantity and then a covariance function. And in the cases that I'll show, it's a Gaussian covariance function. So this quantity here, the covariance function, can be something other than a Gaussian covariance. So it can be anything. So one way to think about these Gaussian processes is like a Gaussian distribution that also has a mean and a variance, and then so this has a mean process and a covariance to it rather than just the variance. So it's similar, you can think of it similarly to that. So this is just a simple schematic of what I've just referred to. I'm using one parameter. So we have a parameter x, so it has various values that went into the 4 simulations, and we have some metric on the y-axis here. So we get 4 values coming out of the simulator. And then there's the mean process portion, and then the Gaussian process that is trying to fit the points in this manner. So there's these, they're supposed to be green, but they don't really look green here. So, and around each one of these curves here, there's a variance associated. So it's not just one little curve here, there's a spread, especially around the tails of these curves. So then the black line is just that, the mean through all of these quantities. So between the first and second points, there's a large uncertainty in this area, a relatively large uncertainty, while between the third and fourth points is a much smaller uncertainty in what the solution should be. So you could look at this and you could say, well, that's kind of like spline fitting. And in fact, spline fitting is a simple Gaussian process itself. So then if we just take a simple example with a real model rather than just a schematic. This is using an energy balance model. This is the model of John Shepard's. So we're varying the solar input parameter, just one parameter, and looking at the output temperature Y. So in this case, we had 5 realizations of the energy balance model represented by the stars, varying this solar parameter. And then the emulator then gives us this black line here with the uncertainty about that line represented by the gray lines. So we can also, because this is such a simple model, we can also compare it to a Monte Carlo method. So it's going to be really hard to tell the difference in the colors, but the histogram of the temperature is shown here, both for the emulator, which are the black lines, and the Monte Carlo estimates by the gray bars. And you can see that there's a pretty similar comparisons in the PDFs. And so gives you some confidence that this sort of method might work on a more complicated problem. So if we look then at using the same energy balance model and looking at 2 parameters, so we're looking at the solar parameter and the eddy diffusivity parameter. Again, looking at the outcome for the temperature, we produce the PDF, and then we can also look at the influence of each of these parameters on the solution. So we get a smaller influence on the solution from the eddy parameter, represented by this red dashed line here, and then the solar parameter is represented by the black line. And you can then also try to look at the interaction between these two quantities. And again, it's looking at nonlinear interactions.
Is it nonlinearity is here through the albedo?
Excuse
Only
me?
The nonlinearity is through the albedo and through the long wave radiation only? Or
I don't know the details of that energy balance
albedo,
model.
it should be linear in the solar forcing. We can talk about it later.
Yeah. So on the problem that I'm working on, this feasibility study, for a full climate GCM, you have your various components, the ocean and ice and the atmosphere, and then there would be another bubble here for land that's not on these. And you have various contributions to the uncertainty. So you have model parameters, initial conditions, boundary conditions, and then the numerics or the structure of the model itself all can contribute to the uncertainty on whatever outcome you're looking at, be it the overturning, the surface temperature, etc. So to reduce some of the complexity of the study, I'm only looking at the model parameter space. So this is a perturbed physics type of experiment, and only in the ocean and ice components. And for initial conditions, all the runs will have the same initial conditions. The boundary conditions will be all the same, and the model numerics and structure is the same. So why look at the parameter space? This is the plot by Cox and Stevenson. And they tried to estimate the contribution in a climate model from the various components. So 20% of the uncertainty they contributed to the process or parameter uncertainty in a climate model. And for the initial conditions, they were influencing this is the orange line here, influencing the solution from the beginning of the run, where they have a big contribution to the uncertainty, and then it tails off towards the end. And then the scenario uncertainty, or this can be thought of as the forcing function. And so that has a small influence at the beginning and then slowly increases. So we're dealing with an ocean model, so this type of figure might be different. But again, even if it's 20%, that's a good portion of the uncertainty, and just try to understand this part of the uncertainty is a reasonable problem to look at. So the problem that I'm looking at is using the CCSM. This is NCAR's GCM at 3 degrees. So it has a resolution or grid points of 116 by 125 levels. So it's quite coarse in terms of ocean models. It has an active ocean and ice components. This is the POP ocean model, it's a parallel ocean program model that comes out of Los Alamos, and the sea ice model that they've developed also. So I'm using NCEP interannual forcing at the surface, and I want to create a 100-member ensemble, each member having 100 years in length. And then I'm looking at 9 parameters. And so I did an initial design phase that had 10 runs, and then the full experiment phase has 100 runs. And then if there's time, I'll do a 10-member ensemble run at 1 degree using the same model, this CCSM 3 and 25 levels. So just to give some examples of some of the parameterizations in the ocean model, the POP model. So we have the vertical mixing parameterization, and that's Bill Large's effort. And then the Gent-McWilliams parameterization or scheme. So this is to look at the added advection term that relates to how eddies are influencing transport in the model. And I'll get back to a comment later on the vertical mixing. So this is just the set of parameters across the top that I'm varying, and then the runs for the initial 10 run experiment. So,
did you choose those values uniformly within the minimum and maximum bounds?
yes.
And did you sometimes transform first? For example, quantities that are strictly positive and operate on a logarithmic scale. Usually we would choose linearly within the log bounds.
So what I did was to take a minimum and maximum based on other people's work of looking at, say, the vertical mixing schemes, and then I just used that Sobol sequence to sample the space.
Right, so you didn't transform any of the parameters before you did your
experiment. For these each ensemble member, I'm saving the full three-dimensional space of the model for every month. So I have values for temperature, salinity, the velocity fields, sea surface height, and there's also some diagnostics that are calculated as the model runs along, that go along with that. So for the various metrics that you could examine pretty much anything you want, because I'm saving the full model space every single month. So not only means can be looked at, but variances. So this just gives you an example of some of the things. The surface temperature. This won't probably change between the model runs very much because I'm using surface forcing that's the same for every run. Then there's the mixed layer depth, the transports. You could look at heat content, currents, overturning, etc. I'm sure others want to look at other things. And at some point, when I get through the runs, they'll be available for anybody to use also. So these are 2 runs just to give an example of how the runs are differing in the initial experiment. This is sea surface height, and then there's a difference of a couple centimeters between these 2 runs. This is surface temperature, the mixed layer depth, and then the velocity. And then this is just the overturning structure at 30 degrees north in the Atlantic. And this also, I'll mention that this is just the last 60 years of the run. And you can see there's still probably some drift in the model, and I'll have to consider the drift when I'm doing my analysis and determining which realizations of the model I can use in the ensemble creation.
Why is the drift there? Because you start probably from a spin-up.
Yeah, I've started from a spin-up, but there's still some drift. And so I haven't tried to, so the initial conditions of all the runs is the same field. So there's some drift from that field. I guess there's been some thought or discussions that you could change the parameters, try to spin up the model, and then start looking at the analysis. And that just added too much computation time, so I couldn't do that.
So initially there's sort of a thumb, is there, where the,
Yes.
yeah,
Yeah.
where the model adjusts the different parameters.
Yes. So I took those, so at the time these plots were created, I had 20 runs done, and these 20 runs are not necessarily spaced evenly across the parameter space, because they're just the ones I've completed at that time. So this figure down here is the distribution of the sample points for 3 of the parameters. Even though I'm varying 9, I just can't show 9. So that the open dots are the points that haven't been done. The black dots are the ones that have been completed. And the black dots are the ones that have gone into the emulation calculation, and the red dot is a completed realization that has not been included in the emulation. So this is the histogram of, for this metric, the North Atlantic wintertime mixed layer depth. The black dots are where the GCM values are, and then it's kind of hard to see here. The red dot here is the one realization that has not been included in the emulator creation. So you get a sort of interesting distribution for this, and I would not say that's probably what the final distribution would look like, but this is what it is for this set of inputs and sampling. This figure down here is actually the emulation and the emulator space. So that there's actually 3 parameters here. So one parameter on the y-axis, one along the x, and then the metric is actually the vertical axes, and the color is the metric. But then there's a third metric in here that's actually the thickness of this surface. And then the dots are just showing that the GCM, the output that comes from the GCM fall within this emulator space itself. So we can look at how these changing these parameters influence the solution. And for this solution of mixed layer depth, it's primarily the KPP diffusivity quantity, or actually the GM diffusivity represented by the red line. And then there's some influence by the black line, which is the KPP. The anisotropic viscosity quantity here is the blue line, and it doesn't have much influence on the solution at all. So this shows both a linear and a nonlinear response in the emulator from varying these parameters. We can look at another one, the MOC in the North Atlantic. This is at 26 north. And we can see again, the 3 different parameters. And this one, the primary influence on the solution is the KPP quantity. And it's a fairly linear response to it. So, and again, this is the sampling that was used, and then the emulator space. And it's fairly Gaussian, I guess. But also what I plotted up here are some values from the multi-model CMIP simulations, and I'll make some comments about these.
If I would have guessed a priori, I would have thought that the MOC would be much more sensitive to GM than to KPP.
Yeah.
The mixed layer the other way around.
Yeah.
So
Yeah.
Is it the mixed layer up in the northern latitudes where the water's sinking? Is that being handled by KPP?
Yeah.
Is that the reason?
Well, I haven't looked into the details of why these things are happening, and I might make the same assumption, but again, these are just 20 of the whole 100 that are needed, so the final picture may look different. So I'm not. It's just an example. A couple weeks at the workshop that was held, there was discussion about multi-model ensemble, and I mentioned something about what I call the genealogy, or Bert Sentner calls the genealogy of models, and how there's a lot of interrelationship of multi-models. So this is just the ocean model genealogy, and it's basically the U.S. models, and this is after a figure that Bert Sentner created in the 90s. So you have this set of ocean models that are primarily the basis for all ocean models, I think, the Brian Cox and then Bert Sentner's work. And from all of that, these others have derived. This is Bert Sentner's work when he was at NCAR and MPS. Primarily, this is just taking the Cox model and parallelizing it to run on the Cray, and then changing resolutions and adding a few more things. And then it stopped because there was changes to computer architecture, and NCAR didn't get a new massively parallel computer. So there was work put into the POP model, which is a multiprocessor type of a model. And there's a tight correlation between Bert Sentner's work here and the work that went on at Los Alamos. And then, so here we have, this is the UK set of models, and then the GFDL MOM models had their own line. And then NCAR set of models, of course, these were running on a Cray at this time, and then we had the switch in computer architecture, and they decided to use the POP model then in their new generation of climate models, so the CCSM and CESM. So there's the contributions, like from the UK, Peter Kilworth's free surface went into POCM, and then it also had some influence on what was done with POP, although there's differences. This is the global model that came out of David Webb's work. And then the current model that's being used in the UK for the HADGEM model, this is the French ocean model, and it has its basis somewhere along this line coming from the Brian Cox work, but I'm not sure what that derivation is. But
I think it was developed independently.
well, it's not what I.
On the cigarettes, and it's a different grid also.
Yeah, but somewhere it's probably up, maybe up here.
The French do always everything independent.
Right, but I guess at some point they looked at what Brian and Cox so somewhere is coming down, and so this is what's in the HADGEM model. But I just sort of added that to sort of place it somewhere in this line. So if we could just think about vertical mixing, then there's various types of vertical mixing that could happen in the models, Krauss-Turner, the KPP, and then second order Meller-Yamada. Most of the models in the climate world, ocean models, are using the KPP parameterization. Although one of the ones that I'll be showing is using the Meller-Yamada, and the GISS model might be using Krauss-Turner, but I'm not sure. So there's sort of variations in which mixing scheme you use, but also probably maybe in the details of the parameterization. So I just looked at several models from the CMIP archive, the GISS model, the Canadian, a Japanese model, NOAA, GFDL, the Hadley model, NCAR's model, and then you also calculated the overturning for the POCM at a 1/4 degree resolution. And that's what these stars or symbols up here represent. And so you can see that the outcome of the perturbed physics experiment shows a broad distribution in the solution, and it covers most of these points here except for this last star, and I'd have to go back and look at which model that was. And the hindcast run falls, it's about 11 along this plot, so it's about right here. But then all of these models are much less than the overturning that is calculated by observations from Bryden, and that's somewhere out in this area. But there's a difference in how those calculations are done, so a direct comparison has to be done carefully on that. So I think that we can look at the uncertainty in a GCM using these types of methods, because we can look at both linear and nonlinear effects. And then the next steps, I want to say a couple things about that. So I'm doing this run up here using POP CCSM, the 3, with POP 2 at 25 levels, 3 degrees. I'll create this emulator, and then I'll try to do this one at 1 degree using the information that comes out of this first emulator plus 10 runs coming out of the second emulator at a higher resolution. And I'm pretty confident that we can say something about this 1 degree model based on the information we find out from the 3 degrees and these 10 runs. And next I'd like to look at the new POP model that's running in the new NCAR climate model, the CESM. So that's looking at that at 1 degree, but it has 40 levels and it has some new physics in it also. So whether or not you can say something about uncertainty in this new POP model based on this emulator and this emulator is quite uncertain in my view. And then once you have all this sort of information, can you even say anything about other multi-models, and if they're only run 1 or 2 other times, is there any information that's transferable into understanding uncertainty in those models? So that's a question that I have. So the long-term goal is just to look at this low resolution to high resolution and see if you can look at uncertainty between those sorts of things. Run a full CCSM, looking also at atmospheric parameters. And then this is work that I'm trying to get the Navy interested in, is to look at uncertainty in the initial conditions. So trying to understand uncertainty on the shorter time scales of several months or interannual type of uncertainty. So, thank you. Question? Yeah?
When you're choosing the models that you include in the emulator, do you test any of the models become realistic in some sense?
Yes, that's sort of where I'm at right now. I'm going through the runs and looking at the solution in a pretty broad sense, and if things don't make sense, I won't use it in the emulation. Yeah.
I'm not sure that 100 years is enough time for your parameters to really be reflected in the output from your model. In previous work people have been doing is to use 300 years or 500 years, and they're still inadequate. So have you any plans to run some long-term experiments to sort of check some of these?
Not at this time. So I've run 200 years before to get to the initial conditions, and then there's this 100 years. So
It's 300 total, not
But
100.
just to clarify, that 200 years, is that not with the different parameter values?
right. It's not changing. So
One thing that just to
Why
add,
don't you-
following on, I just want to, because I think it's directly relevant. I wonder if you could look at building your emulator based on, say, the 50 to 60 year decade, and then build it on the 90 to 100 year decade, and see if your emulator looks different, because that might indicate how much this drift is affecting things.
that's
It's
a good idea. Yeah.
Because I have the same concern.
Right.
Or
Right.
emulate the difference and see if it's on average error.
Right. Yeah, it's just setting up this problem, trying to justify doing it in the first place was kind of a difficult hurdle to overcome in the U.S. And then getting the computer time necessary also kind of limited the length of time necessary, and just getting the runs done is a big enough effort. So.
Yeah, it's always a practical problem. But, I mean, 100 is really short, I think.
Right, but I think there's enough information in there that will be useful, like just looking at the different solutions at this point.
I think you
So-
find it very difficult to get it accepted without some longer runs. I've been involved in the review process of several of these papers, and they're always saying you need longer runs. So I really recommend you do a few.
Okay, well, I'm not trying to look at the climate sort of problem at the end, just trying to see whether or not you can actually use these techniques to understand uncertainty and in the parameter space. So.
Well, it depends on the quantity also. I mean, if you have the MOC, you would need very long runs. So if you're looking at the mixed layer depth, probably much shorter runs.
Right. Yeah, and it's just an experiment, so we'll see.
So how long does it take you to do 100 years?
Depends on what computer I'm using. So on the fastest computer at in-car, it's an IBM something, it takes 2 days, or probably 3 days really with, in real time. I'm also using a machine at the Navy school, which is a much slower one, and that takes several weeks to do it. So.
Just testing the concept, could you just use the North Atlantic model instead to check out the ideas rather than the global model?
I could have,
When you
but
considered that.
I guess there were a lot of different options on how to approach a problem, and this is the option that I chose. So, and I think one of the things this gives me is an ability to go forward and look at different resolutions, and then tie it in with the work that's going on at in-car. So,
Actually, the question of using different resolutions is very relevant. I think there's a paper by Kian and Jeff Wu, about this. They call it low accuracy and high accuracy experiments. And then you can borrow strength across resolutions.
mm-hmm.
And therefore you can run less high accuracy runs. That's a good way to do it.
We've done that with the clump experiment, where we've run most of our runs with a slab ocean,
Mm-hmm.
and we've done a small number with a dynamical ocean. And
But you're just looking at the atmosphere.
You've got atmosphere and land parameters. Yeah. And what we've done is we've co-emulated those two sets of runs in one emulator. So we've unified them within a larger emulator where there's an additional parameter which is a switch. It switches between a slab ocean and a dynamic ocean.
Oh, okay.
Yeah. So we've done hundreds of runs of the slab variant and 17 runs for each era for the couple. Yeah.
Okay.
I'll check the research about that. Can I just come back to Julie's point? Because I mean, I think this is a serious issue actually, especially with the thump that you get from not spinning up each particular parameter combination. So one thing that we've speculated about doing but never actually done is estimating the first few EOX from the long control run.
Mm-hmm.
Yeah. And then emulating the spun up condition in terms of its coefficients on the first few EOX. The idea is that it won't take you exactly to where, so you make a new choice for the parameters. But you have an emulator that tells you roughly what the initial conditions should be in terms of a weighted combination of the first few EOX from the controller. It doesn't get you all the way to the spun up values for those particular parameters, but it does put you in the right ballpark. So that it accelerates the second stage
Yeah,
of the spin up and changes the initial.
I mean, I still think you're going to see a change at the first part because even when you run with different forcing products, you get a big change. I mean,
this doesn't solve your problem. It's just designed to speed up.
Yeah.
As well, there's a whole field of research in people trying to devise ways of effectively spinning up much quicker by not just integrating through time, but finding a fixed point via
Right.
more algebraic methods. And people have done it with ocean models. I don't think anybody's quite done it with a full GCM coupled to the atmosphere. The problem is that at different timescales, but these methods sort of might be worth looking into, I guess.
Right.
Samar Katiwala, that's right. Is it something?
Any other questions? No, thank you.
Thank you very much.